Bueno, es un placer para mí que tengan invitado a Yuri Tschinkel, es un líder en el área de se ven números en filosofía matemática. Eso hay un trabajo que tiene que ver con encontrar profesionales en variedades, un poquito con el original de pregunta, que encontrar profesionales en variedad, no la orientación de trabajo. Es un área muy activa, se ha desarrollado muchísimo en los últimos 20 años. Hizo su doctorado en MIT, su profesor fue en Maine, y ha estado en varios ramos importantes, y desde hace 10 años trabaja en la Universidad de Nueva York, en NYU. So le damos la bienvenida, welcome to Mexico, thanks for visiting us.
Yes, good morning. Thank you very much for the invitation and hosting me here. This is my first visit to Mexico City. I'm delighted to be here. About my talk, half this talk will be historical. I've been at the University of Göttingen for 5 years, and this is a library. This is in fact the first mathematics institute in the world that was built as a mathematics institute, supported by the Rockefeller Foundation at the time, and you see the original design, the tables, and the books. And I found notes of seminars and lectures from 19th century and classics. In particular, a lot of information about the giants of mathematics who worked there. Went back to Gauss, and then Dirichlet, Riemann, and then Hilbert and Minkowski, of course Klein. So the first half of the talk will be about Minkowski. In particular, in June last year, it was 150th anniversary since his birth. And well, that was an occasion for me to go back and to the notes that there. And I wrote a short piece for the Nápoles of the German Mathematical Society, Mathematical Society, that just appeared. And then the second half of my talk will be about, if you like, modern research, or some of the questions and problems that interest me, and connect in one way or another to the work of Minkowski. Right. So here is a young Hermann Minkowski. A little bit about his family. One of his ancestors was quite distinguished. First he studied law and was a judge. Then he decided that he wanted to do medicine. And he went to England and studied medicine. And he became a doctor to a noble family. But all this time he was interested in, well, for example, mathematics. He published the translation of Euclid, 6 volumes of Euclid, from Greek into Hebrew, trying to make this more accessible. Now, some of the descendants of this distinguished person took the name Minkowski, and then the grandson of that was the father of Hermann Minkowski. So the family lived in what is today Belarusia, not very far from Minsk originally. Alex Sultan is in fact a small town that is now close to Kaunas. All those countries, they were changing, the borders were changing all the time. It was hard to know which country are you a citizen of. So sometimes it was Poland, sometimes it was Russia, Tsarist Russia. In any event, around the 1870s, the family decided to leave Russia, that Aristotle was part of Russia at the time, and to move to Königsberg, which was Germany at the time. And this is where Hermann Minkowski grew up. So there were several siblings. I will talk a little bit about Minkowski's brother later on, but so here is a very short version of Minkowski's CV. He studied in Königsberg. He spent some time in Berlin, at the University of Berlin. He won very early in his life the Grand Prix of the French Academy, which was a big international distinction that immediately put him at the forefront of mathematics at that time. He did his army service, he became a non-tenured professor in Bonn, then moved back to Königsberg, where he had a real chair, a professorship. Then he spent some time in Zurich. He came to Göttingen and died in his early 40s of ruptured appendicitis. So this is a very moving obituary by Hilbert for Minkowski. So what happened is that this was actually an amazing time for the mathematics in Göttingen. Klein, Hilbert, Minkowski were very close personally. They worked together, they had joint seminars, and what happened is that for 6 years, every Thursday, punctually at 3 p.m., we took our mathematical walk, as we did last Thursday. On Sunday, he suffered a ruptured appendicitis, and he passed away on Tuesday noon. This Thursday, a week later, again at 3 p.m., we have buried him. So it came completely out of the blue, out of the sudden. They operated on him, it was too late, he died. He died as he lived, as a philosopher. Several hours before his death, he was still proofreading his papers. He deplored his fate, as he could have done so much more, but he was also saying that his latest work on electrodynamics would perhaps benefit from his withdrawal. So this is his grave in Berlin. You see also the name Oskar Minkowski. He was a brother who was a doctor. In fact, he discovered the connection between diabetes and pancreas, doing some experiments in dogs. So very famous physician at the time. And they were in Berlin. Now you see this, there's some button to push here, this red brick here. This is a sign that this particular grave yard is sort of an honorary grave of the city of Berlin. Every 25 years, the city reconsiders this distinction, as it did last summer. And in spite of intense lobbying by the Berlin mathematical community, they decided not to extend this designation. So I was there as well, so I gave this talks that you were here today. I wrote a letter to the mayor of the city of Berlin, asking him to indeed reconsider this decision. And I got a very, very long response to the fact that Minkowski is important and famous, but not as famous as some other actors and writers that are designated as. Anyways, that that battle was lost, and the only satisfaction I have from the process that about 2 weeks after this exchange of letters, the mayor of Berlin had to step down. And somehow I'm convinced that I had something to do with it. But, well, this is the last time you will see. And this is Minkowski's house in Göttingen, where he lived from 1902 to 1909. Now, he died, life continues. Here are posting a note about his successor in Göttingen, Minkowski, Landau, the analytic number theory, and he starts teaching distribution of prime numbers, and then a joint seminar with Silver, and goes on. So I already mentioned that Minkowski became very, very famous by solving a problem. In fact, the problem of Eisenstein. Now, Eisenstein, as you can see, they're very young. But already at this young age, he was very famous in Germany. He was a member of the Berlin Academy of Sciences, the Göttingen Academy of Sciences. Famous people at that time, Gauss and Humboldt, they had very, very high regard for him. Now, the problem that Eisenstein posed in this one-page note in the journal of Pure and Applied Mathematics, or Cuándo journal, pronounced the Mathematik. The problem was, well, is there a formula for the number of representations of the number m, an integer m, as a sum of 5 squares? All right. So there are some conjectures here, and well, that was a problem. Now, Minkowski, in Königsberg, where he grew up, where he went to his high school, in fact, that high school was a very, very special school. It was founded maybe in the 15th century. I mean, it's one of the oldest high schools, gymnasiums in Germany. And it had an extensive library. For example, it had this Kröller journal in the library. So the students in this high school had access to latest mathematics. And there is no doubt that Minkowski was, in fact, reading those publications. Famous scientists went through this high school. For example, Hilbert and Minkowski were friends at this high school. And also Sommerfeld and many others. So, in these days, it's not even obvious for a math institute to have the Kröller journal in the library. In fact, in Göttingen, we had to defend this journal from being cancelled. So, now, the French Academy formulated this problem of Einstein as one of these prize problems. So here is a problem, please solve. Of course, the problem was that it has, in fact, been solved some 20 years earlier by a famous English mathematician, Smith, Henry Smith. And it had been published in the leading journal in England. In fact, at the time when the problem was formulated, Smith was, well, not only a famous mathematician, but in fact a member of many societies, scientific organizations. So let me tell you a little bit more about Smith. So he was the president of the London Mathematical Society. He was appointed to 2 royal commissions. He was the head of the meteorological office of the UK, of England. And, well, so there is sort of a nice obituary for him and his collected works that are also found in the library. So we are reading about him that he was a tall, good-looking man, renowned for his charm, generosity, warmth, and spontaneous wit. He, for example, was appointed to fellowship, Corpus Christi College, and then he writes that the office gave him a pleasant house, a small stipend, and not very uncongenial duties, half as master, half as servant. Then he, for example, writes on some other occasion that so he had some office in London that he had to attend to, and he writes, well, this letter work was specially congenial, and the associates at this new office were so considerate and able as to give a charm to toil that Henry Smith enjoyed the fortnightly visits to London and the temporary rest from the turmoil of Oxford business, which is sort of fun to read these days. He had to escape the turmoil of Oxford and, you know, get some rest and respite at London. Now, so he sees the prize problem advertised by the French Academy and he's complete disbelief. I already solved it 20 years ago. So first he consults with his colleagues. What should I do about this? So he writes, well, need I write to Hermite or to the others in France? Is there anything I should do about this? And after some conversations with his colleagues, so he decides to write to the French. Now, I wanted to show you the first page of this paper where he solves the problem. And as you can see, the very first word is Einstein. The very first word in this paper. You know, and it's documented here. So he's a little annoyed, and you know, I have given this complete series not only for 5 squares but also for 7 squares. He says I solved it, you know, in much more general form. and I have a general theory, and do I need to do anything in the matter? So my first impression is that I ought to write to Hermite. Well, so a line or two of advice would really oblige me. So he writes to Hermite. He says, Mon cher monsieur, well, and Hermite writes back, well, it's of course a mistake of the commission, we are very sorry, but please submit, your work with many more details. And by the way, it has to be in French. So he's a distinguished senior academician, so he decides to write up his thing one more time. And while he's doing this, he goes horse riding, falls off a horse and dies. All right. Now, of course, Hermite keeps saying that, oh, it's not my fault, and we don't really know. So the end result is that the Academy gives two prizes to a paper by Minkowski sent from faraway Königsberg, this 19-year-old young, very, very young person, and then to Smith, who's already dead. Now, of course, huge scandals in the French newspapers because this is around the time of the French-German War. And, well, they're giving the prize to a German, and he didn't write his thing in French. He sent in a manuscript in German, and I've actually seen this manuscript, and it says, well, I'm really sorry, I don't have time to translate this into French. So please accept it as it is. So the story, well, is what it is. Jean-Pierre Serre wrote in the Gazette Mathématique, some 10, 15 years ago, that, well, the Academy, apart from the mistake of not having read Smith's work, made an excellent choice. Minkowski's results were used by Siegel and by many others, and by Andrew Vail in his theory of adelic groups. The subject is still very active. And so we have seen, so here, je termine, nous avons vu un mathématicien allemand, we have seen a German mathematician who wrote in French, so that was Einstein. An English mathematician who does the same, members of the Academy who don't read English, but give a prize to a paper written in German. Doesn't it mean that the languages are not as important as ideas? So that's that. Now, a little bit more about Minkowski as he grew up. So he's now a non-tenured professor in Bonn. He talks about his life in Bonn, about teaching. These are his letters. This is his handwriting. I mean, the letters are available in the library. I'm getting it. And, well, he says, I have some listeners who are pretty strong, but overall in Bonn, it is quite frustrating to communicate with my mathematical colleagues. One complains about headache all the time. With another, his wife steps in every 5 minutes to turn the conversation to something else. And so he's not very happy in Bonn. And moved on to Königsberg. Well, Königsberg, so that's him at the time of his moves, already a young professor. He's not that happy either, and after a while he moves to Zurich. Now, this whole hiring process at Zurich, his appointment first at the university, then at the newly established ETH, the technical school. Well, there is sort of a long story here, but the bottom line is that, so he understands, of course, that people in Zurich want to attract Hilbert, but Hilbert is not movable, and so he writes to Hilbert, well, surely if they could have gotten you, they would have taken you, but now, well, they take me. Now he says, Zurich is wonderful, and, well, we continue. But soon after he gets to Zurich, the reality of teaching hits him. For example, here he writes to Hilbert, well, I have in my math lectures -4 students, but here in brackets he writes this is a dash and not a minus sign. And after a while, he is totally frustrated and says, in spite of all my efforts to adjust to the level of students and preparations for my lectures, I have fewer and fewer listeners. Even the mathematicians, of which there are very few, are so busy with various administrative tasks that they can only swallow what is forcibly shoveled down their throats. And now he says, well, I really want to move out of Zurich. So his colleagues, of course, realize his frustration with everything, and they appoint him as the head of the entertainment committee of the International Congress of Mathematicians in Zurich. So, another thing I learned from this exchange that I didn't know before. So, 1896 was this Congress in Zurich, and then there was a Congress in Paris, 1900. And well, Hilbert is consulting with Minkowski, what should he talk about at this Congress. And so there is this letter from January, where Minkowski says, what will really make a difference is if you, just a second, if you talk about problems, if you formulate problems that will occupy the minds of the mathematicians later on. He writes, themes that are of philosophical nature are perhaps more suitable for the German audience rather than the French. But you should think about these problems. And so, at least from this exchange, I have the feeling that Minkowski suggested to Hilbert that you should. Now, Hilbert formulates the problems and sends them back to Minkowski, and then there's a letter coming back to the effect that I can only congratulate you on this lecture, and I am very sure that these talks that you will give, it will be read by every young mathematician without exception, and it will have impact for decades, if not centuries. It's sort of unbelievable how so these sparks of genius in Minkowski, this foresight. Now, let me keep going. So this is this is what I just told you. Your talk. I have read your talk with a lot of interest and Vortrag habe ich gelesen, and I can only congratulate you on. And this will be the main event of the Congress, and success and so on. All right. So this is the book Geometry of Numbers that Minkowski gave to Klein. Here it means to Professor Klein. Geometry of Numbers. And there are some remarks of Minkowski about number theory. So these days we hear about arithmetization of all branches of mathematics. Some think that arithmetic is only a reasonable state government, so to speak, for the huge state of mathematics. At last, some will see arithmetic only as the high police, the secret police, that is in control of all those hidden paths in the empire of functions and numbers. Well, I can say that a true arithmetician is an enthusiast per se. Without enthusiasm, there will be no arithmetic. And in general, I feel that very optimistic for number theory. And I have the hope, I still have the hopes, that very soon, from all the other fields, from physics and chemistry, we will hear praises for the pure numbers theory. Well, for example, where people will recognize that essential properties of matter are in connection with, for example, the decomposition of primes as sums of two squares. And on those days, arithmetic will be the key of everything. Now, of course, what does it mean, decomposition of primes into sum of two squares? When you study this as the simplest instance of reciprocity. This is quadratic reciprocity. Alright, so if we continue this path, reciprocity, its modern incarnation is the Langlands problem, the geometric Langlands problem. Well, mathematical physicists, they do think that Langlands program has some relevance to what they are doing. At the Institute of Advanced Study in Princeton, the Langlands program is a big topic with physicists, Clinton, Rafa, and others looking at this into detail. So, and this is Minkowski 100 years ago. It's kind of unbelievable, his vision of what is to come. So now I want to talk more about mathematics and about the Minkowski-Hasse principle. So if you take a form, an equation, homogeneous, of degree 2, and with rational coefficients, and you ask, when does it have solutions in the rationals? Of course, it will have a trivial solution, 0, 0, 0. It's a homogeneous equation. But when does it have non-trivial solutions? Well, the principle says that it will happen if it has solutions in the reals and in the p-items, which means modulo p. Okay, what about forms of higher degree? There are counterexamples. In the counterexamples, you can write them down, cubic equations like this, or more variables. This is a cubic curve, this is a cubic surface. So that was one theme of interest to Minkowski. Another theme of interest to him, he was deeply interested in interactions between rigid objects, for example, numbers, integers. So when you think of integers, you think of them as, well, points on a line, so like a rigid thing, or you could think of a lattice in some high-dimensional space, vector space. So look at vectors with integral coordinates, integer coordinates. Well, so it's a lattice point. And so Minkowski was thinking about lattices. So these are notes from his seminars in Göttingen. So you see these lattices, and then you see these shapes. So arithmetic geometry, it's about the interactions between rigid objects, lattices, and geometric objects. So the geometry comes in through these equations. The equations describe some geometric shapes. And then the question is, well, how much can you read off from the geometry, from global geometric invariance? How much do you learn about arithmetic properties? And vice versa. What does arithmetic tell us about geometry? So, so here is the famous theorem of Minkowski. So you see some lattice point and you see some shape. And so what's this theorem? So let's look at the lattice in R2. So a lattice is a lattice, right? So a lattice. Now, the co-volume of a lattice is, well, it's a volume of a fundamental parallelepiped for the lattice. And suppose it has co-volume 1, just normalize the measures, area. Now, let's pick anybody, a convex, symmetric domain. Symmetric means that if x is in the domain, minus x in the domains. And convex means that if x and y are in the domain, then the interval between x and y is also completely in the domain. And the only thing to require that the area of this domain is bigger than 4. Then, and this is Minkowski's theorem, we are guaranteed to have at least one more lattice point in this domain. So this is an example of this interaction between geometry, in this case metric geometry. I mean, you have some area, you don't know anything about this domain, it's some domain, you don't know anything, except these two conditions, and you're forced to have a lattice point inside. So I learned about this theorem in high school. So these are my notes, my own, this is a proof in my high school handwriting, in my high school notes. So this is all that it takes to prove this is out. But it has, as simple as it sounds, it has far-reaching applications to problems in, for example, algebraic number theory. Let me give you a sample problem. So there is a notion of number fields. So number fields are, well, they're essentially vector spaces over the rationals. But so in a vector space you can add. But here you can also multiply. So how do you multiply it? Well, this alpha that is sort of spanning this vector space, it satisfies an equation with rational coefficients of degree d. Which means that alpha to the d can be expressed as a linear combination of, well, these rational coefficients of all the previous powers of alpha. So in this vector space you can multiply, you can easily show that you can divide. So this is a field. It's like the real numbers. The rational numbers, just something in between. Now once you have a field, you're doing arithmetic, you want to know what is an integer. Well, if the rational is an integer, it's an integer, 0, 1, 2. Here an integer is something that satisfies an equation where the first coefficient is 1, and all the other coefficients are integers rather than rational numbers. Now, it's not obvious that two such things multiplied and added are again satisfying this condition. In any event, this is a ring. So now you want to understand something about arithmetic in this ring. Well, there's a notion of a discriminant. So if you pick a polynomial of some degree d, you look at all its roots. Then you start writing down symmetric functions in its roots. Well, the standard symmetric functions, of course, are the coefficients. This, for example, is a product of all the roots. And this is the sum of all the roots. Some, plus minus. But if you look at this symmetric expression, well, it is something. It can be written in terms of these coefficients by a fundamental theorem of symmetric functions. This is called discriminant. Now, the lattice point theorem of Minkowski says that there are no extensions of the rationals with discriminant equal to 1. Now, if I give you an equation, for example this one, a cubic equation, and I write down the discriminant of this equation, here it is, minus 4p cubed minus 27q squared, and I ask you, can you show that this equation equals 1, this expression equals 1, has no solutions in the integers? It's not going to be easy. This is not something that you can ask high school students to do. It follows from Minkowski's lattice point theorem. And this is just the case degree 3. In degree n, as you can imagine, these are very complicated Diophantine equations. And Minkowski tells you there are no solutions. Just from this geometric considerations. Of course, to get here, you have to work. Alright, so here are some recent conjectures about these discriminants. So you can look at all extensions of degree d, you fix the degree, ordered by the size of the discriminant. And you can ask, well, how many of those do we have? And the conjecture is that it's linear in B, where B is the bound on the size. So what is known? If D is 2, what is the discriminant of a quadratic extension? So a quadratic extension is simply Q adjoins square root of D, where D is square root. And the discriminant is either D or 4D. So if you are asked to count D's, so that either D or 4D is less than B, and also is square free, well, it's very easy to see that it's linear growth. So it's really B. The conjecture is trivial for D equals 2. But for D equals 3 already it is non-trivial, and it's a big result, classical result, that you have it. Now Manju Bhargava, in his thesis, proved the conjecture for D equals 4 and 5. So this was the first big breakthrough since the 70s. And, well, for this and also for his later work on elliptic curves, he got the Fields Medal last year at the Congress in Seoul. Now, for higher Ds, the conjecture is quite open. There is a bound, which is very weak. It's better than a naive bound. It goes back to Ellenberg-Ventratesh. So this is something that is of interest. Now, once you think about lattices and lattices in space, you can ask, well, what is the best way to pack shapes of equal size into space? For example, spheres. So this is a paper by Minkowski that addresses this. And by the way, this is also a problem of Hilbert. It's one of Hilbert's problems. about the most efficient packing of space by shapes of equal shape. Now, of course, in the special case when the shape is a sphere, it's a problem of Kepler. And, well, what is better, this or this packing? And this problem has been solved by Hales and his students. Now, there was a huge manuscript. It relied on computer computations, so many, many thousand lines of code. It was submitted to the Annals of Mathematics at the time when I was visiting the Institute of Advanced Study, and I saw at lunch all these discussions. The editors did not know what to do. So they sent the paper out to 20 referees. The referees wrote back, we are almost certain whatever we have checked seems plausible, but we can't be sure. We cannot be sure that there is a proof. So Hales decided to develop a separate language, a separate machine that would check his original proof. So this effort took another many, many years. Last May, there was a presentation at the Simons Foundation where Kepler spoke about the history of the problem and about the recent history as well. And in particular, checking the proof is impossible. So after 50 years, he was still not finished at the formal level. He was almost finished, and by August of last year, I mean by August 14, he was actually finished. Finished in the sense that there is a separate language that can go and check sort of every single subroutine and formally. Now, of course, there are people in the audience saying, well, suppose, so you're relying on a computer for proof checking. Suppose, the sun hits the disk and some electron jumps the other way and the computer gives something else. I mean, do we really have a proof? What does it mean to have a proof? Well, of course it can happen. Computers can fail, you can get it wrong. So it's, in the end, a side development has nothing to do with Kepler's conjecture, but which pushes the limits as to what constitutes truth and how important is it to know that the obvious sphere packing that Kepler knew about is really the optimal one. Once you think about rigid figures and space, you also think about polytopes. And this is another paper of Minkowski. So here are some polytopes. The these look kind of symmetrical, so here are more. But here is one that you may not have seen. It occurs in nature. So you pick some algae and you magnify 4,000 times, and this is what you see. It sort of happens by itself. It prefers this particular shape for some reason. Now, so what's the connection between polytopes and lattice points? So a polytope, you pick finitely many points, and you take the convex hull. We already talked about convexity. And then you may blow up this whole thing. Just multiply everything by some scalar factor, and then you ask yourself, well, how many lattice points are we going to have inside? Now, let's denote by times the number of lattice points. It turns out that to understand this purely arithmetic, if you like, counting problem, you need to deploy algebraic geometry and topology. So you have to appeal to the theory of toric varieties. You start with this polyhedron, polytope, and the lattice that you cook up a toric variety out of this, plus a line bundle on it. I need to know what it is, but the number that you're seeking is actually the number of space of global sections of this line bundle, and that is given to you by something called the Riemann-Roch formula. And that gives you the formula. Now, in the end, the formula depends only on topological invariance of this variety. So this is rather unexpected as a connection. But you can ask another purely combinatorial problem that has nothing to do with anything. So let's look at the faces. Let's count the number of edges and two-dimensional faces of this polytope and so on and so on. Let's organize these numbers in a vector. So what can we say about these numbers? And the solution, going back to Richard Stanley at MIT, again, you appeal to toric varieties, and now you deploy something called intersection homology, and that gives you relations between these numbers. Also unexpected. The purely combinatorial problem is translated into topology. So I just wrote down some other applications of polytopes, the way polytopes appear in modern mathematics, of course in combinatorics, but also in analysis, in a series of hypergeometric functions. There's a famous book by Gelfand, Kapanov, and Zelevinsky. You look at asymptotics of some integrals, oscillatory integrals, and so on. You want to understand this, and you realize polytopes play a role, and toric rises. In topology, in particular in tropical geometry, began somehow the complicated geometry is reduced to polytopes. In the numerative geometry in Gromov-Witten theory, again, polytopes play a role, and in something that's closer to my own interest in algebraic geometry. Well, if you look at the resolution of singularities, at the minimal model program, at, for example, cones of amplitude effective variables, again and again, polytopes appear, and we need to know this kind of combinatorics. Something totally unexpected to me was the connection between Minkowski spacetime and airplane boarding. So, Minkowski spacetime, by the way, when Minkowski was complaining about his students in Zurich, how bad they were, and that they never came to his lectures, so one of his students was Einstein, and who himself then wrote about Minkowski. Well, Minkowski was the first who attempted to teach mathematical physics to us. And Minkowski again talked about Einstein and said, well, with Einstein, he never came to my lectures. He was so lazy, I would have never thought that he was capable of relativity. Now, when you look at this relativity, what do you have? You have this, what they call Lorentz metric, x squared plus y squared plus z squared is t squared. Now, just think about it. Minkowski in his childhood was thinking about representations of numbers, the sum of 3 squares first, and then 5 squares. Well, how do you think about 3 squares and 5 squares? So on one side you have m, or t, and on the other side you have sum of squares. And then Minkowski connects this somehow to geometry. So to Minkowski, with space-time geometry, there was a problem in numbers theory. It was totally natural for him to think about, okay, well, integers, so you can do real numbers. So you do geometry on this space, it works. And that turned out to be the key idea, special relativity and so on, like really key observation that there is this, what we call Minkowski geometry now. What is not so obvious is that the same geometry shows up in a problem called airplane boarding. So Eitan Bachmet, the first author of this paper, he was my friend. MIT, we were graduate students together, we were sitting in the same office. He was working in arithmetic geometry, he was a student of Davidson. But at that time, a company emerged in Boston called EMC. Now it's the biggest supplier of storage systems. They sell 30 billion worth of storage systems a year. Huge, huge company in Boston. Now, storage systems, it's many rotating disks. And they asked him, well, can you come up with some algorithms? How do you access random points in some efficient manner? Ethan says, I don't know anything about computers, I never programmed. Well, okay, let me think about it. Anyway, he thought about it, some friends of his programmed this, and made $100 million in improvements, profits to his company, because you save a little bit, some epsilon in your estimates, and immediately it's translated for all these many disks rotating. It's an advance, He realized, Ethan, that actually accessing points on the rotating disks or boarding airplanes is the same problem. What happens when you board airplanes is that, well, there is, people try to get in, and there is some person standing in the aisle and is trying to put luggage, and well, nobody can pass, right? And then, somebody else, of course, moves on, and the next ones they can either distribute before somehow, or if they hit the wall, if they have to get a seat further on, well then. So he realized that this is actually Minkowski space. Not being able to pass through the person in the aisle, it's like sitting inside the light cone. You can't get through the light cone. So once you start thinking in these terms, you can model the process. He does it, and he has a mathematical theorem, and of course, with error terms, that the most optimal way to board an airplane is actually random access. Okay. Now you come to the airport and you see group A, group B, group 1, 2, 3, 5, 7, 8, this, that, and the other, complete nonsense. So, and he you can do it numerically, you can simulate this, there's a theorem that does it. In fact, he came recently to the foundation. We had a very interesting phone call with some bosses from American Airlines. So they had 10 people on the other side, so 8 of them, sitting there talking. And the person opens the conversation, some kind of leader there. They are very interested in advances in theory, best ways to do business. And the end of the conversation was, well, thank you very much. You have interesting ideas, but we will stick to our process. We will do what we are doing, and that's it. Nevertheless, this is some kind of unexpected connection, right? I mean, this is how things are. Another unexpected connection, Adam says, well, we can actually compute those boarding times. To compute the boarding time, well, it's an elliptic integral. But you can also introduce parameters in the game where you say, well, some people, half the people, they're that fast, and some other, portion of the people, they have a different, time that they have to spend putting those things in there. It depends on, you can do more subtle analysis where you say, there are younger people, there are older people, this and that. All right, so let's look at the next case. So the next case that we looked at, compute the boarding time. Well, so Ethan writes down equations and say, wait a minute. It's a surface. What kind of surfaces do I know? It's a case 3 surface. So the boarding time in the next model is essentially a period of a case 3 surface. And so on. So mathematics is just behind you. We poke a little bit into its practical world to start thinking not in terms of engineering, but in terms of what is actually happening here. Then, it leads to something. Now, let's go back to quadratic equations, so conics. The theorem of Legendre says that if you have an expression like this with ABC's integers, then to know that your solutions must be, you have to check that, to know that there are solutions in the integers, you check solutions must be and in the reals. Moreover, you can bound the height of the solution. And the height is the maximum coordinates, x, y, z. So we can ask, all right, in general, if you look at more complicated equations, is there something called the local global principle? Can you conclude from solvability mod P and then the real is the global solvability? Then you can ask, well, how many points of bounded height do I have? How many members of this family? You see, it's a family. ABC can be considered as parameters. How many ABCs give you an equation which has solutions? And finally, what is the smallest rational point you can have? The smallest solution. So, well, the Hasse-Minkowski principle already mentioned. There are counterexamples, even for equations like this, for example, for this. And the proofs use more complicated reciprocities. I mentioned quadratic reciprocity. Here you have to use cubic reciprocity, and you have to use the theory of algebraic number fields, in particular the divisibility of class numbers. Now, so here is some complicated diagram that provides higher cohomological abstractions to existence of rational points. And again, I've never seen this, but it's called the Brown-Lyman abstraction. And it's computed, the abstraction group, via some Galois cohomology. Now again, you haven't heard about these things, so this is a finite abelian group. And for equations of interest to us, the abstraction group is either Z mod 2 or Z mod 2 squared. Now, the Galois cohomology for surfaces, and if you're interested in arithmetic of surfaces, can be computed by the Galois action on exceptional curves. The cubic surface, you may have heard, has 27 lines on it. The section of the quadrics has 16 lines on it. They have some interesting symmetry. So the Galois group will act through the symmetry, and the symmetry is actually the Weil group of root system, in this case E5, and in the case of cubic surfaces E6. So this connects to the theory of algebraic groups. Now, the main observation is that when the Galois action is large, the abstraction group is small. There is a conjecture by Polytopes and Saint-Sucre which says that if you have a cubic surface over the rationals, for example, rationally connected surface of a number field, then this Brown-Lyman abstraction is the only one. if what we compute is not empty, there should be rational points. And it has been established, I mean, the conjecture came not out of nothing, it came from some results, that if you have a pencil surface in the intersection of two quadrics that admits a conic bundle, which admits a map onto a projective line, then indeed the obstruction is the only one. But it's still open for general pencil surfaces. Now there's a recent breakthrough here based on additive combinatorics of all things, really honest analytic number theory, that in fact not only such two pencil surfaces, but in fact arbitrary conic or quadric bundles are treatable if all the generated fibers are defined over the rationals. Alright? Now, so do we believe this conjecture? And as I said, the obstruction group should be trivial if the Galois group is large. And that always seemed sort of counterintuitive and implausible to me. If you take your surface and start twisting it arithmetically, you don't expect the arithmetic to become easier. But in fact, this is what the conjecture predicts. So I asked my postdocs in Göttingen to check this on computers, and they came up with thousands of examples of cubic surfaces of the rationals. They computed the abstraction, they looked for points, and the conjecture seems to be true. Now when you're faced with such overwhelming numerical evidence, you go, there must be something behind this, there must be some theory behind this. And so we decided to look at the analog of number fields, any function fields of curves. So in this case, one variable, so over a finite field. And the theorem is that if you have a complete intersection of this type, quartic to pencil surface, a general quartic to pencil surface, over this field, then indeed there are rational points. So, so this is one aspect of the program. Another aspect is let's count these points. So, well, we realize our variety is sitting in some projective space, just one equation, x cubed plus y cubed plus d cubed equals t cubed or something like this. And then let's count the number of points, and let's ask, well, what is the asymptotic as the bound goes to infinity? So here are some cubic surfaces, singular cubic surfaces, different singularities. But in all cases, the conjecture, going back to Mani, predicts b log b to the 6th rational point in common height. So here are some rational points plotted of height less than, I don't know, 1000 on this cubic surface. This equation, all you need to do, plug in integers and count solutions. So, there is a result of my student Derenthal. The asymptotic is some constant times b log b to the 6th as predicted. Now what's the constant? So this is the shape of the constant. Some rational number, something equals to 1. It's not always 1, but still I don't keep it here. It's 1 here. And then a product of densities, local densities, number of points over a finite field over b squared, which is e to the dimension, and regularizing factor. And the constant in infinity is this. So these are the kind of results that people have been establishing for other classes of surfaces in recent years. The general conjecture says that, well, there should be this constant product of these things, and one of the things is rational, another integer, and this Tomagawa number is something. Now, if you look at this conjecture and you ask yourself, all right, what is the smallest solution given this? We don't know this, of course. We know this only in special cases. But if we knew this, how would we go about estimating the height of the smallest point? Again, so the conjecture suggests that it will be 1 over the Tomagawa number, approximately. So I asked Alfonso to write down, look for smallest solutions on these cubic or quartic pencil surfaces. So you get plots like this. I mean, of course, you can always come up with examples where the coefficients are essentially the Tomagawa number, the size of coefficients, where the coefficients are large, but the solution is small. You would take 1001 x cubed minus 1000 y cubed. So clearly, 1 and 1, and then plus z cubed will give you a solution. So we see these sort of exceptionally small things here, but overall you see a pretty sharp line here, right? So there is some conjecture as to what the smallest point should be, that needs to be established. This is just numerics for that. Now, as I showed you already, we can think geometrically over functional fields of curves and arithmetically over the rationals. The idea that rational numbers and fields like f, q of t are closely related, that goes back to Riemann. That's the analogy between numbers and functions. So, when you think about this field, you think of your variety as being fiber over Q1, which in case of rationals would simply mean you fix a model over the integers. And you consider the integers as a curve, rather than the spectrum of the integers. So then you fix the height of the solution, and now rational points are simply sections of this vibration, and in particular, they're actually parameterized by algebraic varieties. And so properties of these varieties, of these spaces of sections, well, they are essential for the understanding of arithmetic properties. And so here is an ideal scenario that Brandon Hassett and I developed, that these spaces of sections should be geometrically irreducible. They should dominate something called the intermediate Jacobian. It's an abelian variety, some analog of elliptic curves in higher dimensions. And the spaces should fiber over intermediate Jacobians, this general fiber, the rational connected variety. So this is some kind of uniform description of those spaces of sections. And we can prove this in some cases with Brandon Hassett, and in some other cases, recent work of Lausanne shows that it just kind of works. There are real abstractions to this first, to the third statement in the ideal scenario. So this is very briefly as to what I'm doing right now and how it connects to the classical mathematics, local global principles, understanding rational points, and understanding them in the geometric context. Thank you.
¿Hay preguntas o comentarios? Hacemos otra vez conferencista. Me recuerda la película Dónde 15, él es el productor de la película y es para público en general. Es un documental sobre diversas cosas.